Today I'm providing feedback on the aqueous equilibria worksheet. Okay, question number 1 gives you the pKa, and it's asking you about the ratio of acetic acid to acetate that you would need to prepare a buffer with a pH of 4.50. Okay, you'd use the buffer equation, pH equals pKa plus the log of the ratio of base to acid. Okay, so what we're solving for is this ratio. Okay, so we're given the pH, we're given the pKa, and that difference is negative 0.24, which is the log of this ratio. And if we take 10 to the minus 0.24, we get 0.575. That's for the base to acid ratio. The question is asking acid to base, but if you give either answer, that is okay. Okay, this one you would also use the buffer equation. You'd substitute 0.45 for base, 0.5 for the acid, take the log of that, add it to the Ka, and you get 4.69. Okay, part C. Okay, what you do here is you, since the acid and base have the same volume, okay, those can divide out. And if we take concentration times volume, okay, so 0.45 times 100, that's 45. 0.5 times 100 is 50. And then if we convert 0.005 moles to millimoles, as we add sodium hydroxide, that's going to increase the number of moles of base, or millimoles of base, and decrease the millimoles of acid by the same amount. Okay, so this is so in the numerator we have 45 plus 5, in the denominator we have 50 minus 5, and if we solve we get 4.79 for the pH. Okay, and we can see that the pH has changed very little. Okay, so we went from 4.69 to 4.79. And our pH should go up since it's becoming more basic. Okay, with this one we do the same way. Again, 0.45 times 100 is 45. And this time we would reduce the millimoles of base by 3, and we would increase the millimoles of acid by 3. And our pH now is 4.64. Okay, question number 2. Okay, so this is asking us to calculate the molar solubilities for copper 2 phosphate. KSP is 1.4 times 10 to the minus 37th. The KSP expression would be copper 2 cubed times phosphate squared. And when this dissociates, we'll get 3 copper 2s and 2 phosphates. And so KSP would be 3x the quantity cubed times 2x the quantity squared, okay, which, if we combine terms, gives us 108 times x to the 5th. Okay, solving for x, we would divide by 108 and then take the 5th root of the result. So that's 1.67 times 10 to the minus 8th molar. Part B is we work it the same way, but this is simpler. When silver iodide dissociates, we get one silver, one iodide. Okay, each one of these is X, and so KSP is X squared. And if we just take the square root of the KSP, we get our solubility. Okay, question number 3, we're going in the opposite direction. Cadmium carbonate has a KSP of 1.0 times 10 to the minus 6th. And that shouldn't be molar. Okay, so let me take that off. Oh, yeah, I'm sorry, it is molar. We're calculating KSP. Okay, so this is X. This is a 1-to-1 ratio. And so this should be just X squared. Okay, part B. Okay, we're given the solubility in grams per liter. If we divide by the molecular weight, grams cancels out, and we get moles per liter, or molarity. And so that is our X. Since this is a 1-to-2 ratio, lead is X, bromide is 2X, and we square the 2X, so combining terms, this is 4X cubed. And so our KSP is 6.61 times 10 to the minus 6th. Okay, number 4, this is a common ion effect. Okay, so we have strontium fluoride dissolving. It's producing a strontium plus 2 ion and 2 fluorides. This is the KSP. Okay, and so the question is asking, what is the solubility in 0.01 molar strontium nitrate? Okay, so we take our KSP, and without the added strontium, this would be just X times 2X the quantity squared. Okay, X is just from the strontium fluoride dissolving, and then the 0.01 is from the added strontium. And we can assume that in this term, the X is going to be small, so this simplifies to 0.010 times 4X squared. Right, so we divide both sides by 0.010, we divide both sides by 4, we take the square root, and X is 2.55 times 10 to the minus 4th. Okay, part B, this is also a common ion. Okay, here we have the KSP. Without the added fluoride, this would just be X times 2X the quantity squared, or 4X cubed. Okay, but this is from the added sodium fluoride. We can simplify. We can assume that the 2X is small. And so this simplifies to X times 0.010 the quantity squared. Solving for X, we get 2.6 times 10 to the minus 5th molar. All right, question number 4. Will a precipitate of barium sulfate form when 100 milliliters of 4.0 times 10 to the minus 3rd molar barium and 300 milliliters of 6 times 10 to the minus 4th sulfate are mixed? Okay, so what we need to do, we need to calculate the concentrations of both the barium and the sulfate. Okay, so first we need to calculate the number of millimoles. Okay, so we take concentration times volume, and milliliters will cancel out, so we get 0.4 millimoles of barium. And the concentration of, the millimoles of sulfate, again, we do that the same way, concentration times volume. So that's 0.18 millimoles. And then to find the concentrations, we take these amounts in millimoles divided by the total volume. Okay, so we added 100 to 300, so our total volume is 400 milliliters. So we have to divide both of these by 400. The Q expression looks just like the K expression. It's the barium concentration times the sulfate concentration. And we come up with 4.5 times 10 to the negative eighth. Okay, the KSP is given. That's 1.1 times 10 to the minus 10th. This product, Q or IP, is 4.5 times 10 to the minus eighth. Because Q is greater than K, a precipitate will form. Okay, if you only say yes or no, there's no credit. Okay, you have to calculate Q. Right, number 5. This is a question involving mixing a strong acid and a strong base. All right, so we start out with 40 milliliters of 0.1 molar HCl. 40 times 0.1 would be 4 millimoles. And then we're going to add 20 millimoles of 0.1 molar NaOH. Okay, so that's 2 millimoles. Okay, so the 2 millimoles of sodium hydroxide are going to neutralize 2 millimoles of HCl. Okay, so that means that we have 2 millimoles remaining. Okay, so that's the amount, and we divide that by the total volume, which would be 40 plus 20 is 60. And that would be the concentration of HCl. And since HCl is a strong acid, that's also the hydronium concentration. So that's 0.0333. And if we take minus the log of that, 1.48. Okay, at part B, we're at the equivalence point, and so the pH would be 7. Part C, we're beyond the equivalence point. Okay, so we've added 4.5 millimoles of sodium hydroxide, and 4 millimoles of that was neutralized by the HCl, so we have 0.5 millimoles left over. We divide that by the total volume, which would be 40 plus 45, or 85. And that gives us a concentration of hydroxide of 5.88 times 10 to the minus third molar. If we take minus the log of that, that's the POH. 14 minus the POH is the pH. Okay, so 11.77. Okay, so this should be a number greater than 7 since it is a solution that involves an excess of OH. Okay, question number 6. We're titrating ammonia, which is a weak base, with hydrochloric acid, which is a strong acid. And at the equivalence point, all of the ammonia is converted to its conjugate acid, ammonium. And then ammonium then does a back dissociation until equilibrium is reached. Okay, if we take 30 milliliters times 30 millimoles per milliliter, we get 9 millimoles. And since we're at the equivalence point, we'll also have 9 millimoles of ammonium. And we divide this by the total volume, which is 30 plus 30. So 9 divided by 60 is 0.15 molar. Okay, so that's going to go in the initial for ammonium. Okay, when ammonium back dissociates, it will decrease by X, and ammonia and hydronium will both increase by X. Okay, the pKa of ammonium is 9.25. The Ka is 10 to the minus 9.25, or 5.62 times 10 to the minus 10th. Ka would be it'd be ammonia times hydronium over NH4 plus. So it would be X squared over 0.15 minus X. Okay, let's assume that X in the denominator is small. So this simplifies to X squared over 0.15. And so X is 9.18 times 10 to the minus 6th. Okay, so X is indeed small compared to 0.15. Okay, if we take minus the log of that, that's 5.04 for the pH. Okay, for part B, what is the pH halfway to the equivalence point? Okay, we could set up another ice chart, or we could simply recognize that this is in a buffer region, and halfway to the equivalence point, we have converted exactly half of the ammonia to its conjugate base. So the base and acid concentrations would be equal. So this ratio is 1, log of 1 is 0, pH equals pKa. And so pH equals the pKa, which we set up here was 9.25. Okay, question number 7. Benzoic acid, 1.22 grams, is dissolved in 0.1 liters of water. Okay, you can use millimoles per milliliter if you want. The molecular weight of benzoic acid is 122.12. Okay, so what is the amount of benzoic acid in moles? Okay, so if we divide the mass by the molecular weight, grams divides out, and we get an answer in moles. Or if we use milligrams and millimoles per milliliter, or millimoles per milligrams per millimole, then we get an answer in moles or millimoles. Okay, so what is the concentration? Okay, concentration is amount divided by volume. Okay, so the amount, okay, you could take 0.00999 moles divided by 0.1 liters, or you could take the millimoles divided by milliliters. Either way, you should get the same answer. Okay, this answer goes in the ice chart below. Okay, and then this is going to dissociate partially. We'll start out with no hydronium, no conjugate base. The Ka is given, and that is equal to hydronium times A minus over HA. Okay, so that's X times X, or X squared divided by 0.0999 minus X. Which is, okay, and we can make an approximation here. So X is 2.54 times 10 to the minus third. Okay. So what is the amount of sodium hydroxide in moles or millimoles that's required to neutralize the solution? Okay, because at the equivalence point, the moles of acid is equivalent to the moles of base, they're going to be the same number. Okay, halfway to the equivalence point, again, pH equals pKa. Okay, if we titrate with 0.0250 molar NaOH, what volume in liters or milliliters is required to reach the equivalence point? Okay, so volume is amount divided by concentration. And of course, we get a ridiculous answer, 400 milliliters. We would have to empty the burette multiple times. Okay, so the combined solution would be 100 plus 400 is 500. And the concentration would be 9.99 divided by 500 milliliters, which is 0.02. Okay, and then we would enter that into the ice chart. Okay, this time we have a base rather than an acid. So we've converted all of the acid to its conjugate base, and then the base starts to back dissociate. And this time when we solve for X, that's actually going to be the OH. The KB, we would calculate that from the Ka. We would take Kw divided by the Ka, that's up here. And if we take x squared divided by 0.020 minus x, we can simplify that. So x is 1.76 times 10 to the minus 6. Okay, so POH is minus the log of that, and then pH is 14 minus that.